This is Lab 6, off-axis aberrations, and the purpose of this lab is to investigate off-axis aberrations such as coma and astigmatism. And so what we're trying to do in this lab is to actually manually find the wavefront coefficients. This is the general form of the wavefront aberrations. And we see in this diagram that we can actually add up all the wavefront aberrations in this form. In this lab, we'll be investigating W131 and W222. This is coma and astigmatism, which are off-axis aberrations.
So here we have coma, which occurs when magnification of an optical system varies with pupil position and field height. As you can see here, for an exclusively coma system, it is the aberration is equal to W sub 131 times H times rho cubed times cosine theta. Here is a simple system, a singlet system with the marginal and chief rays traced out, and you can see that coma is in essence where the marginal rays intersect and the difference at that point where the chief ray is. Now, two crucial things about coma is that there is none for an on-axis field, and it linearly increases with field height. Right here in the tangential ray fan, you can see here that there is zero error at zero and negatively quadratically increases as field height increases. And for the sagittal ray trace, there is absolutely no error.
The second type of aberration that we focused on was astigmatism, which is also an off-axis aberration. The wavefront coefficient for astigmatism is represented as this W222, and astigmatism occurs when the tangential and sagittal rays focus at different positions. So the sagittal rays are in the YZ plane, and the tangential rays are in the XZ plane. It's kind of hard to see in this picture. And sagittal focus, it's key to note that it coincides with paraxial focus, which is why there's zero sagittal ray error at all fields. The tangential ray error exists for fields that are not zero. So at the zero field, this is actually equal to zero also. And as you shift from tangential focus to sagittal focus, you notice that we have a horizontal line for tangential focus, and it goes through and it hits medial focus. Then you have sagittal focus, which is a vertical line. And that's because when you image a point source with astigmatism, you will actually have perpendicular lines at your focus. And medial focus, the diameter, if you want to know this, is given by this. And you can relate this to the defocus wavefront coefficient through this equation.
It is worth noting that even as we move off axis, both spherical aberration and defocus contribute to the total net aberration, as we can see here. However, if we put the focus point at marginal focus, we have that W040 equals -2 with W020. And so as we move off axis, we get this equation for when we're talking about coma at x equals 0, and at x equals 1, this all blows, these two cancel out when y equals 1, and we get that total aberration is only contains coma.
The setup in this lab was similar to last lab, except in this lab we used a beam expander. This was to fill the entire aperture of our test lens in order to measure or study off-axis aberrations. A mirror was used, and this allowed an extra degree of freedom and allowed us to scan through our Hartmann mask. This is the entire setup. And the Hartmann mask we used had holes in the vertical and horizontal planes, as this was to map the sagittal and tangential rays. And once the image looked like this is exaggerated, but the left and right holes should be inverted along with the up and bottom. And to find marginal focus, we made all these dots converge into one, which formed a gridiron interference pattern. The wavefront coefficients calculated were about 10 waves for tangential coma and about 3.5 waves for sagittal coma. For astigmatism, tangential, it was about 16 waves, and sagittal astigmatism was about 80 waves. And these values are a little high.